Let's look at the most famous optimizer in neural networks, Adam optimizer. I will explain 4 different formulas, how it regulates size, step size, how it adjusts every gradient based on previous gradients, the average, the magnitude, and why it learns so well. You can check the timestamps of the YouTube video to find key points and structure to the video. After understanding this, you will understand the most famous optimizer, most commonly used, and it will be a very solid foundation for understanding every other optimizer. Prerequisite for this video is for you to understand what are weights in neural network, what is loss in neural network, and maybe it will be good if you understand how gradient descent works and what a gradient is, but I'll try to explain that as well. Let's take a look at the Adam optimizer. Let's say you have some loss surface and you wanna change your weights such that you go down this loss, you minimize the loss. So that's how neural network learns. You change the weights of the neural network so the loss, the error between the predicted outcome and the correct outcome or correct answer is minimal, close to 0. So this function is the function of the loss. So depending on your weights, on your numbers in neural network, you're gonna be somewhere here on this surface on the loss, and you wanna change weights to go down, so loss is close to 0. But you don't know which direction is down, so you will calculate that with gradients. Gradients will show you which direction you need to go up. So if you subtract that direction, it will go down, because gradient will show you the steepest up direction. So if you subtract, it will show you the opposite, down direction. Now, every batch of data, the small part of data that you use to update the weights, is its gradient may not be exactly the same as the gradient of the entire dataset. So this small batch of data will actually have a bit different gradient. It will not be 100% representative, it will be a bit different, maybe some niche. You could say that every batch of data has its own loss function, which is maybe similar to overall in all of the entire dataset, but it's a bit different. So when you calculate in which direction to move based on every part of batch, part of dataset or batch of dataset, it will be similar to the entire dataset, but it will not be 100% same. So there will be a bit of noise. So when you will move a bit randomly on the landscape from the perspective of the entire dataset. If you go straight down on the batch loss data. The idea here is that on average, all of these small batches should point towards general minimum of the loss function of the whole dataset, because on average these random movements are gonna average out. So we wanna use this instead of just making updates based on current batch that can be a bit different and not so representative or a bit random. We also want to use how the previous batches made the gradients move. So the momentum, because the idea is that this momentum will prevent random or too much random oscillation. So it will minimize random oscillation. It will make every batch kind of go a little bit more in the average direction of every other batch, but it will also have its own unique direction added. It's like if you're trying to take average height of 10,000 people and you have some average height, and then if you take any 100 random people, their average height might be a bit different than the average of 10,000 because there might be a bit more taller people. So that difference in average is the noise of every group of 100 people compared to the entire 10,000 people average. And that's how our batches and mini batches work compared to entire dataset and their gradients. The true best gradient you would get if you could pass entire dataset. But since you cannot, you need to pass bit by bit, and there will be some noise in these gradients. So Adam Optimizer, besides looking at the current gradient of the current batch, it will also look at the past gradients and average them out, and then fix the current gradient, the direction of the current gradient, using the past average as well. But not too much, because current gradient could actually provide valuable information as well. Adam in particular is using exponential moving average, and I'm gonna show you some examples here written by Gemini which are very good. So we do want to average out past gradients, but we want to give more strength to the latest gradients. Maybe because model was smarter when it was making them, for example. Also because we might be changing the direction, so we don't want the old direction to influence too much the newest direction. So this will calculate the kind of average direction we are going. The gradients are showing how we should move weights to go down the loss, like this direction where we should go. And you see here that we need to change direction, so we don't want this part of the direction to strongly influence this part, so we want to actually decay a bit more the very old parts and their influence. So this is how we calculate the average. So we say the new average is equal, or the new direction or average is equal to the some hyperparameter beta that's between 0 and 1, and the higher it is, the more of the old average we keep in the new average, plus 1 minus. So if this is 0.8, this will be 0.2 times new value. So now new value the latest gradient will carry maybe 20% of the weight of the new average, and old values will carry maybe 80%. So if this is beta is very high, then older values have stronger influence on the new direction or the new average. And if beta is low, then new value will actually be stronger and pull stronger in its direction. And these are hyperparameters that need tuning, so you need to tune them to test different values to see, based on your dataset and model, which ones are good and work best for you. The difference can be even like 20, 30, or even more percent faster training. You can say that beta is a smoothing factor or decay rate. It's a number between 0 and 1 that controls the memory of the average, how much of the old average we keep and how much of the new. So if it's very high, like 0.9, then a lot of the old average is kept, and this will be smooth direction. It will not be so changing direction, average direction here. And if it's like just 10%, then the new value, the noise of the new value can be changing it a bit left, right, up, down, a little bit more. And Adam will keep two separate exponential moving averages for each parameter in the model. This is why Adam takes a lot of memory. So the first moment is exponential moving average of the gradients themselves. The second moment is of squared gradients. The first moment is what I just explained. We keep the average of a few past gradients, so we eliminate some random noise of new gradients moving randomly, while still letting the new gradients contribute to the overall direction. And then the second moment, the square of the gradient. You know, when you square something, the bigger it is, it's gonna become a lot bigger the bigger it is. Square makes big things a lot bigger and small things a little bit bigger. Before we dive deeper in that square and second moment, let's take a look at the 4 steps that Adam does for every single weight at every step. 4 calculations, I should say. Update the first moment, what I just explained. We have the old average and the new gradient times 1 minus beta. It's gonna give us the new average, the new moment. And then update the second moment, which is gonna be second beta parameter, different hyperparameter, and then times old second moment, and 1 minus beta 2 times squared gradient. So it's almost the same as this one, besides we have different hyperparameter and it's square gradient and not the just the normal first power gradient. The next thing I will also explain on the first moment, but exact same thing applies to second moment. So just understand what first moment does. It's easy to understand second. It will be easy to understand second as well. We will have a problem at the beginning of the training with this exponential moving average, because let's say we initialized it with 0. So at the beginning, this average is 0. And if you check the formula, so let's say our beta is 0.9, 90% of the old average, but in the beginning it's 0, 0.9 times 0, plus 0.1 times new gradient. This is the problem. The new gradient is just now 10% of this first gradient at the beginning, because we don't have anything before. So this is the problem, like intuitively. The average after the first gradient should be the first gradient itself. Or even if we are calculating some maybe a bit smaller average, we can reduce it a little bit, whatever. But this is extremely weak average, weak, it's not strong, it's just 10% of this gradient. And in the next step, it will have a weak influence on correcting the gradient because it's very small. So this way, in the beginning of the training, this average will be tiny number, and it will have very weak influence into fixing the randomness of every next gradient update. And later it will slowly grow, and then it will become stronger, and it will be larger part of the new update, and it will fix the randomness of the latest update. But in the beginning, we're gonna solve it in the following way. So t is the time step of the current gradient update. So in the beginning, it's number 1, the first gradient update, the second, the third. And so with this formula, we will strengthen, increase this average in the beginning of the training, make it stronger, bigger. And later we will not increase it so much. So I don't want to bother you too much with maths, but we are dividing the average with some number. And because in the beginning of the training, we want this average to become a lot bigger. So we will divide it with some very small number, maybe 0.1. So this average will become 10 times bigger when we divide it with 0.1. So in this formula, this will just yield small numbers close to 0. Depending on this time step t. If time step t is low in the beginning of the training, this formula will yield small numbers. You can check. I will show you below example. And later in the training, when this time step t is larger, this will yield numbers that are closer to 1. So it will be, this will make the average almost the same, because we are dividing with like 1 or almost 1. So it will not change the average too much later in the training. When we don't need to change it too much, it's already large enough. And I can show you like example calculations of how it works. In the beginning, it divides the average by 0.9, which makes it 10 times. It's like multiplying with 10. And later it will divide it by 1 at time step 100. And then it's gonna be almost the same. So because this is almost 1, it's like this number, 0.99997. So now we fixed this problem of the very small value of the average at the beginning, because it's initialized by 0 and then multiplied and stuff. And we will do the exact same thing for the second momentum, make it a lot, strengthen it in the beginning, because it's also initialized at 0. So we will strengthen it in the beginning, and then later we will not touch it so much. And by strengthen, I mean increase its value, like from 0.5 to 1, 2, 3, whatever. And finally, let's understand what second moment actually does. So this is the full formula for updating weights, or so this is a single weight, and this formula is applied to every weight. Okay, so we have the current weight that we want to update. Here it's denoted a weight of t minus 1 as if the previous weight of the previous step. And this is the weight of the current step that we are now trying to update. And we will subtract this, which is our gradient. So by subtracting that, we will move down this loss function. So we will change the weights so our output goes like output is not so different. The difference between our output and the correct answer is minimal. But first of all, learning rate. The problem with gradients is they are too big. So if we just subtracted the gradient, we would make too big of a step. Learning rate is like some number that's 0.01. So we multiply gradient with 0.01 to make it 100 times smaller and then subtract it from the weight. And this will lead to convergence to better, faster learning because gradient itself is too big. So what is our gradient? So I shouldn't maybe call it gradient because now it's different things. So now it's this smoothed direction which contains the latest gradient and the exponential moving average of the previous gradients, the kind of average movement direction of the previous gradients that we just explained. This is the first moment. And this is the second moment, which controls the scale, how much or how little we will move in this direction. First of all, this epsilon is a small number just to make sure we don't divide with 0. That's it. That's what epsilon does, nothing else. And now let's look at this. So if the neural network starts moving this weight by big jumps, moving it a lot, this will kick in and start reducing the scale, the size of those steps. So this is the direction of the step, this is the size of the step. And if recently there was a lot of big steps, this guy will kick in and regulate it, make it smaller. Also, if there was a lot of small steps, this guy will kick in and make it a bit bigger or bigger. So it's like a regulator that will keep it balanced. If it's too big, it will bring it down a lot. If it's a bit bigger, it will bring it down just a little bit, etc. You remember how this second moment is calculated. It's calculated with squaring the gradient. So as I said, if the bigger the gradient, the square of that will be a lot bigger. So this makes it sensitive to scale. So this makes it understand the scale of gradient a lot bigger because we are squaring it, so it will just be more sensitive to scale. It will have different reactions to different types of different numbers, different scales. And so check this out. If the few latest gradients were all big numbers, then this, which would be like an average of the squares of those big numbers, average of squares of big numbers, so you are squaring big numbers, so this will be a very big number. And then the root of a big number will also be big. So you are dividing the movement direction with a big number. So we will actually reduce the step size now because it's divided by a big number. So in short, if recently we had a lot of big jumps, then we will divide by the big number this direction, this step, and we make it smaller. And same goes opposite direction. If recently we had maybe a lot of small steps, then root of a small number will be small. So we will divide this with a small number, which will make it then bigger. So this will kind of regulate. If it's too big, we'll make it smaller. If it's too small, we'll make it bigger. Or if it's a bit small, a bit big, then it's gonna maybe keep it kind of same. It's not gonna change it as much. And same goes opposite direction. If recently we had maybe a lot of small steps, then root of a small number will be small. So we will divide this with a small number, which will make it then bigger. So this will kind of regulate. If it's too big, we'll make it smaller. If it's too small, we'll make it bigger. Or if it's a bit small, a bit big, then it's gonna maybe keep it kind of same. It's not gonna change it as much. And this is just how neural networks are seen to work best empirically with experiments. Too big updates, too big steps, it may just overshoot and jump over entire minimum and go on to like some other hill, or too small steps would make it move so slowly and not learn fast enough. So you can also look at this as same as learning rate, similar as learning rate, where learning rate is making everything smaller, but learning rate is same for every weight, and this is per weight regularization, and it can not only make smaller but make steps bigger if necessary. If it's moving too slowly, it's gonna make it bigger. If it's moving too fast, jumping too much, it's gonna make it smaller. So that will be it for this video. Join my school to become AI researcher, link below the video. There are all of these courses and community and new courses coming and lessons coming all the time.